Hi, this lesson is about implicit differentiation. To understand implicit differentiation, we have to understand the difference between an explicitly defined function or an implicitly defined function or equation. Not all implicitly defined equations are functions, but it basically, for the most part, means that you can't isolate your independent variable on one side or that your x's and y's are on the same side of the equation. So these are examples of explicitly defined functions and their corresponding implicitly defined functions or equations. So the linear equation 3x minus 2 can be expressed as 3x plus y equals 2. The two radicals here, y equals square root of 36 minus x squared, or y equals negative square root of 36 minus x squared, as an implicitly defined equation, it's x squared plus y squared equals 36. That's a circle. So the reason why it's not a function and just an equation is because a circle fails the vertical line test. If you draw a vertical line, you'll touch the circle at 2 points. And the last one is a function y equals 1 over x can be expressed implicitly as xy equals 1. When your functions or equation are expressed implicitly, there are a slightly different technique that is applied, but all of the rules that we already know will still be used. Your product rule and chain rule, quotient rule, power rule, etc. are still going to be used, but we're going to have an additional thing to take into consideration. So remember that we can express the derivative with different notation. dy over dx is a common one, and that just means that we're taking the derivative of y with respect to x. And that will be important to keep track of when we're taking derivatives implicitly. First, let's remind ourselves, if I wanted to take the derivative of this, an explicitly defined function, the reason why my y turns into y prime or dy dx is because I'm taking the derivative of y with respect to x. And the derivative of y with respect to x can be written as y prime or dy dx. And on the right side, when I take the derivative of 3x minus 2 with respect to x, I'm really just applying my rules. The derivative of 3x is 3, and the derivative of minus 2 is 0. So 3 plus 0 gives me a derivative of 3. So y prime or dy dx has a derivative of 3. If I did the same problem and I took the derivative on both sides of the equation implicitly, so this is now an implicitly defined function, and I want to find y prime or dy dx. On the left side, I'm taking the derivative of 3x minus y with respect to x, and on the right side, I'm also taking the derivative with respect to x. Well, we know that the derivative of 3x is 3, but that the derivative of y is dy dx, or y prime. So on the left side, I have 3 minus dy dx. And on the right side, the derivative of 2 is 0. Now, to solve for dy dx, subtract 3 and divide by negative 1, so you get dy dx equals 3, which is the same answer we got above. With explicitly defined or implicitly defined, we should be getting the same answer. So here's another example. This is implicitly stated. So I have 5x squared y equals negative 2. So if I apply implicit differentiation to this problem, I'm taking the derivative of 5x squared y with respect to x and the derivative of negative 2 with respect to x. Well, on the left side, I have to apply product rule because this is the product of two variable expressions. So I have my f g prime, so that's 5y squared dy dx, plus f prime, which is 10x, times g, which is y. And on the right side, the derivative of a constant is 0, so that all equals 0. Then I need to solve for dy dx. So I subtract 10xy. And on the next line, I divide both sides by 5x squared. And when I simplify, I find that dy dx is equal to negative 2y over x. It is common to have answers with both variables, both the x and the y, in your derivative when you're applying the implicit differentiation technique. All right, so here's another one. I want to find dy dx implicitly for this equation. So in this case, although my y's are on the left and my x's are on the right, I can't isolate y without having y in my answer. So even if I tried to solve this for y, you would get y on the right side. And so there's no way to isolate y, so you have to use implicit differentiation techniques. So you take the derivative of both sides of the equation, which is exactly what you see here. To take the derivative of 2y cubed, you have to apply power rule. So that's where the 6y squared comes from. But then you have to follow that by the derivative of y. So you have 6y squared dy dx, or you could write it as 6y squared y prime. So think of it as like chain rule, where the cube is your outer function, so you multiply by 3 and subtract 1, but then the y is your inner function, and the derivative of y is dy dx, or y prime. And then the derivative of just y, well, that's just dy dx, so that's your second term. And on the right side, the derivative of 7, that's 0, and the derivative of x to the fourth is 4x cubed. So I have to isolate dy dx. So from this line to this line, we factor out dy dx, leaving me with 6x squared minus 1 inside the bracket, and then divide both sides by 6y squared minus 1. So dy dx is negative 4x cubed over 6y squared minus 1. Okay, here's another one. This is implicitly defined, so we're going to apply implicit differentiation. You take the derivative of both sides of the equation. So the derivative of 8y is just 8 times dy dx. The derivative here, you have to apply product rule, and so the minus sign in front of it is now here in front of this parentheses where I applied product rule. So that's f, and that's the g prime, plus that's the g, and that's the f prime. And so there's your product rule, and then the derivative of your constant is just 0. So on the next line, all I did was I distributed this negative. So you have 8 dy dx minus x dy dx minus y equals 0. Factor out dy dx from these two. So you have dy dx times 8 minus x equals y, and then divide by 8 minus x, so dy dx equals y over 8 minus x. Okay, here's another. So again, you can't just say y equals. If I did try to solve this, when you take the fourth root, you would have plus or minus the fourth root of 3x cubed minus x, which means if you tried to apply this explicitly, you would have two different derivatives. So you're better off leaving it like that and just getting one answer. So using implicit differentiation, the derivative of y to the fourth is 4y cubed y prime, or 4y cubed dy dx. Either notation is fine. And on the right side, the derivative of 3x cubed is 9x squared minus x, so the derivative of x is minus 1. Then divide both sides by 4y cubed, and you get that y prime is equal to 9x squared minus 1 over 4x cubed as a final answer. Okay, here's another. This is implicitly defined, so we're going to find the derivative of cosine of x plus y equal to 1. So the derivative of cosine of x plus y, I have to apply chain rule. Cosine is the outer function, x plus y is the inner. So the derivative of cosine is negative sine of x plus y. Times the derivative of x plus y, which is 1 plus y prime, equals the derivative of 1, which is 0. Then, because we need to solve for y prime, I need to distribute this so that I could have y prime in a separate term. So when I distribute the negative sine of x plus y, you get the following line. And then on the next line, I added this to the right, so that ends up over here. And then because, again, we need to isolate y prime, so we're going to divide both sides by sine of x plus y. So we get negative y prime equals sine of x plus y over sine of x plus y. But we know that this cancels to 1, and then divide both sides by negative 1, you get that y prime is a constant of negative 1. All right, so here's another where we're going to evaluate the derivative at a particular point, and that point is 2, negative 1. And here's our equation, 2y plus 5 minus x squared minus y cubed. So the derivative of 2y is 2y prime. The derivative of 5 is 0. The derivative of minus x squared gives me a minus 2x. And the derivative of minus y cubed is minus 3y squared y prime, equals the derivative of 0 is just 0. Then I have two terms with a y prime, this one and this one, so you factor that out. And the 2x gets moved over to the right, so it turns positive. Then divide both sides by 2 minus y squared, and so I get y prime equals 2x over 2 minus y squared. Then I plug in 2 for x and negative 1 for y, and it simplifies to 4 over negative 1, so that means I have a derivative of negative 4. So a visual of this is the curve is here in red for that equation. The point 2, negative 1 is right here. And so the tangent line is the one in this hot pink kind of color, and that has a slope of negative 4. So that's the point of tangency. It does intersect the curve at a second point over here, but at that particular point, 2, negative 1, that's what the tangent line would look like. Okay, so this is an example of an equation that is not a function. If you drew a vertical line, you would see I would touch the curve at this particular place at 3 different points. So this equation does not represent a function. You wouldn't be able to isolate the y even if you tried. Okay, another example. Here we want to evaluate the derivative at the point 4, 2 for this equation. So to take the derivative of 2 times x plus y to the third, I have to apply chain rule. So that will be 6, multiply the 3 and the 2, and subtract 1 from the exponent. So 6 times x plus y to the second times the derivative of the inside, which is 1 plus y prime, minus. Now, to take the derivative of the second expression, there's a minus in front of this expression in the bracket because I have to apply chain rule. And so that's going to be g, which is x, times f prime, which is 2y prime, minus f, which is y squared, times the derivative of the denominator, which is 1, all over your g, and remember this is your g, to the second power. Okay, so on the next line, what I did was I distributed the 6 times x plus y to the second across here. I also distributed this negative and simplified each of these terms. I separated them out into 2 separate expressions. So I get 6 times x plus y to the second plus 6y prime times x plus y to the second minus 2y prime over x, because this x canceled with one of these, and then plus, and then here nothing canceled, so you just get plus y squared over x squared equals the derivative of 15 is 0. Then I have two terms with y primes. These are the two here in the middle. So I factored that out. And the other two terms, the first one here and this one, were subtracted over to the right. Okay, then I got common denominators. So I got a common denominator for the expression inside the bracket here, which is a common denominator of x. So the first term gets multiplied by x. So I was able to write that as one expression. So I have y prime times 6x times x plus y to the second minus 2y over x. And on the right side, I also got a common denominator, which is x squared. So this term gets multiplied by x squared. So my right side is negative 6x squared times x plus y to the second minus y squared all over x squared. Okay, so I have to isolate y prime, so I'm going to multiply both sides by the reciprocal of this expression. When I do that, it cancels on the left, but on the right, you get what you see here. The expression on the left gets written down and then multiplied by the reciprocal of that expression. And when I do that, there is some simplifying that can be done. So this x cancels with one of these, so I'm left with x. So my numerator is exactly what you see here. But my denominator, this x and this x will combine, and this x gets distributed here. So you get this denominator, 6x squared times x plus y to the second minus 2xy. And now I'm ready to plug in my numbers. Remember, the point is 4, negative 2. So you plug in 4 for the x's and negative 2 for the y's. So you end up with negative 96 times 4 minus 4 divided by 96 times 4 plus 16. When you work that out, that gives you negative 388 over 400. They're both divisible by 4, so simplified, your y prime is negative 97 over 100. And remember what y prime represents. It represents the slope of a tangent line to a curve at a particular point. Okay, so that's it for this lesson. Give the homework a try. Good luck.